Greetings. What I want to look at here is that we have a lot of equations this semester, and we can use the units of constants to help us identify what the equations are and make sure that we understand them correctly. So if I look at an equation of a straight line, y equals mx plus b, b must have the units of y, and m, the constant, must have the units of y divided by x, okay? So for example, if we ignore the b here, we would say that m equals y over x. So if I understand that, I can understand the equation. In other words, the units must line up, and if the units don't line up, then I've got a problem. So what I can say here is something is equal to this constant, okay? And it must have the units of joules per gram degree C. Now I can ask myself, what has the units of joules? Well, joules is energy, so it's either Q or W. Since we're studying heat transfer, it would be a Q. G is the unit of mass, so this would be M. And delta C can either represent a temperature or a change in temperature. We know if we add heat to a substance, its temperature will change or it will undergo a phase transition. So we're going to put here a delta T. So the equation is Q equals mc delta T. Okay? Now I come to my next one. I have a capital C. This is the capacitance of an object. Okay? And it has the units of joules per degree C. So following the logic before, this would be equal to Q over delta T. So it becomes Q equals capital C delta T. Now recognize, capital C is the capacitance of an object. For example, this could be an object of aluminum, okay? MC is saying that the mass of this unit times the specific heat capacity on a per gram basis, okay? So if I know how many grams this is and I multiply it by the specific heat capacity, I get the capacitance. But sometimes we have objects that are of inconsistent composition. And one calculator may be built differently than another calculator, so you just can't measure the calculator and tell it's what the capacitance of another one would be. Now, let's go to these next two, okay? These are enthalpies of vaporization. This is a molar enthalpy of vaporization, and this is a latent specific heat of vaporization. So I could have delta HV, and it has units of kilojoules per mole, okay? So we know that whatever it is equal to is energy, but we're not talking work, so it's heat. And moles, we use the symbol N. So the equation is Q equals N delta H. Okay, now I come over to the second one here, okay? Once again, I have a delta H, a vaporization, but the units are different. Because the units are different, the equation is different. This has the units of megajoule, 10 to the 6th per kilogram, okay? Once again, megajoule, like all along, it would be Q, and then kilogram is mass, 1,000 grams, so this would be M. So here we have Q equals M delta H. So you can't just memorize equations, you've also got to look at the units. And incidentally, these are both measurements of water, and we can convert from one to the other. So let me start with this one here. I have 40.7 kilojoules per mole, okay? Because this is for water, I know that there are 18 grams per mole, so I'll put that in the denominator, 18 grams per mole. My moles cancel. Now I have energy per mass, but these units appear to be different. So I need to convert my kilojoules to megajoules, okay? Kilo is a 10 to the third. This is 10 to the 6th. So I could go 10 to the third kilojoules is a megajoule. And now I need to convert my grams to kilograms. Well, kilo is 10 to the third, because I want kilograms, not grams. So I have 10 to the third grams per kilogram. Okay, I notice that these cancel, the 10s to the third, and I take 40.7, divide by 18, and I get 2.26 megajoules per kilogram. And so these two things are equivalent. It's just one is on a per mass basis, per mole basis, N, and the other is on a per mass basis, M. Okay? Hopefully that helps.